water attack that carbon, that takes you back to where you started. But if the water attacks that carbon, then you go forward and you make isocitrate. And this reaction is also reversible. So you can eliminate water from isocitrate and go back to the citrate. So that's the reaction catalyzed by conatase. Note that water is formed, but it's consumed in the reaction. So there's no net consumption or production of water by this enzyme. Okay. So that gives us isocitrate. And now isocitrate, if you remember the decarboxylation reactions mechanisms, there was beta keto acids and alpha keto acids. And isocitrate is neither one. Right? But we actually saw decarboxylation of a molecule like that in an earlier pathway. And that earlier pathway was the oxidative phase of the pentose phosphate pathway. Right? The last step to make ribulose 5-phosphate was decarboxylation. It was decarboxylation of a molecule that had an OH in the beta position. Right? So the mechanism of this step in this citric acid cycle turns out to be the same exactly. So let me redraw isocitrate. There's isocitrate. And so the first step, catalyzed by the enzyme, it's called isocitrate dehydrogenase, is going to be an oxidation step. The oxidation step involves oxidation of this OH to a carbonyl, reaction we've seen many times. So base grabs a proton, and the H and the 2 electrons are transferred to NAD. That's supposed to be NAD+. Right. And so that's going to give another intermediate. Which is that plus NADH. And so there's the first NADH that's made. And this, again, is an intermediate that's bound in the active site of the enzyme. This intermediate is called oxalosuccinate. And now you see that this is a beta keto acid. Right? So again, using this carboxylate as the reference carbon, there's the alpha position as beta. Okay? So now this can be decarboxylated against chemically relatively easy to decarboxylate. So this forms in the active site of the enzyme. And then it could be decarboxylated like this to give a resonance stabilized carbanion, enolate. And then to finish the reaction, all you have to do is protonate. So grab a proton from the acid in the active site of the enzyme. You get the other product of the reaction. Which is that. So this again is the reaction catalyzed by isocitrate dehydrogenase. And so we've made one CO2. So we need to make 2 CO2s and 3 NADHs. So we made one of the NADHs and one of the CO2s. So again, there's that reaction, isocitrate dehydrogenase. The product here is called alpha ketoglutarate. And now we still need to make a CO2. And remember, the second CO2 is going to come from this carboxylate, which is still there. It's here. And so now this decarboxylation, we know how this will work, because this is an alpha keto acid, right? Got a ketone in the alpha position. And we saw decarboxylation of an alpha keto acid long ago, 2 weeks ago roughly. So what was the enzyme that decarboxylated an alpha keto acid? Pyruvate dehydrogenase. So there's alpha ketoglutarate, often abbreviated alpha Kg. And this is going to be decarboxylated. So this carboxylate will be released as CO2. And the other product is going to be these other 4 carbons, but they're going to be esterified to CoA. So this product is called succinyl-CoA. It's an ester of succinic acid or succinyl-CoA. So there it is, succinyl-CoA, right there. So we need CoA as a reactant. So let's see, we've made a CO2, CoA is our reactant, and again, this is an overall oxidation. Both of these carbons are more oxidized than they started, so we need an oxidizing agent. The oxidizing agent, again, is NAD+, so we'll make an NADH. So we make the second NADH, and we make the second CO2. The enzyme that catalyzes this reaction is called alpha ketoglutarate dehydrogenase. And as I said, if this were pyruvate, that would have to be CH3. If this were pyruvate, the reaction would be exactly the same as what pyruvate dehydrogenase catalyzes. And it turns out that this enzyme, alpha ketoglutarate dehydrogenase, is structurally very similar to pyruvate dehydrogenase. It consists of 3 proteins. One you can call E1, which has diamine pyrophosphate as a coenzyme. It has an E2, which has lipoyolysine or lipoamide as a coenzyme, covalently bound to E2. And it has an E3, which has FAD bound to E3. Right? So just like pyruvate dehydrogenase had an E1, E2, E3, this enzyme does as well. E1 and E2 are different proteins than they were for pyruvate dehydrogenase. So it's not the E3 is actually the same protein in both enzymes, because the E3 actually catalyzes exactly the same reaction in both. E1, this E1 uses alpha ketoglutarate as a substrate, whereas the one pyruvate dehydrogenase uses pyruvate.
But they're the same.
The coenzymes are the same, and the reaction mechanism is exactly the same. So for the mechanism, see pyruvate dehydrogenase. Just write the mechanism that you wrote for pyruvate dehydrogenase, except include these extra 2 carbons. But mechanistically, it's exactly the same. So we don't need to go through it because we all remember it. Yes.
When you were going,
So someone does remember, yes.
so when you were going over these, you were like saying that E1 happened, and then when you had that del sulfide, the lipoamide.
Yeah, lipoamide, right.
You you kind of just extended it and connected it to E2.
Right, it has to swing. Yeah.
So it's at E2 and it's just swing to
Yeah,
E1.
that's right. It has to swing to E1. Reaction percent has to swing to a different E2. The next reaction occurs and it has to swing to E3. And it just, I don't think it knows where to go, but if it gets into the right active site, the right reaction occurs. So it's the same deal.
Oh, so that's what you meant by it. Okay.
Yeah, it has to get into there. Okay. So, all right. So.
Oh, I'm just putting up. Sorry.
That's fine. So, let's say the end of phase 2 is really succinate. So we're almost there, succinyl-CoA. And so now, up here, we took acetyl-CoA, a thioester, high energy. And remember, we made citriol-CoA as an intermediate. Citrate synthase, right? Different mechanism. But remember that citriol-CoA was an intermediate, right? And there I pointed out it's a thioester, so it's high energy, and in principle, we could use that energy to do work, but we didn't do any work up here, right? Remember, the citriol-CoA got hydrolyzed, maybe energy released as heat, and it just made this reaction irreversible. So we said, well, that's probably good. Makes the cycle, once it gets started, it's not going to stop. But down here, we have another thioester. Now here we do work, right? Because you see that we're going to make a GTP, or it's either a GTP or an ATP. It depends on the organism. And that's important, but we're going to use the energy of a thioester to make a GTP. So let's look at that reaction. And so we're talking about is thermodynamically this reaction, succinyl-CoA plus water to make succinate plus CoA. The standard state for energy change for this reaction is apparently minus 33.4 kilojoules per mole. So it's enough free energy to make an ATP or a GTP. As always, the question is, what's the actual mechanism? The mechanism is not hydrolysis. Okay? So I'm going to show you the mechanism, and then I'm going to go through one experiment that provided evidence, a little bit of evidence for that mechanism. So the actual mechanism, as always, rather than hydrolyzing the thioester, which risks sort of losing the energy, instead the energy is sort of preserved during the reaction. So the reaction, this reaction catalyzed by succinyl-CoA synthetase, as shown on the slide. And so the reaction involves the succinyl-CoA binds in the active site of the enzyme. So the enzyme is going to have to catalyze this reaction. That net reaction. So the way it does it, phosphate is a reactant. It's going to use the phosphate as a substrate. It's going to use it as a nucleophile. And it's going to catalyze nucleophilic attack by phosphate on the thioester. Right, so it's a standard nucleophilic attack on a carbonyl, make a tetrahedral intermediate, expel a leaving group. The leaving group is going to be CoA, and the intermediate is this. So we started with a high energy thioester, and now what kind of molecule is this intermediate?
Mixed anhydride.
Phosphor anhydride, mixed anhydride. So this is now high energy intermediate also. So we sort of preserved the free energy of the thioester in the form of the anhydride. Moreover, you could also say that we've activated the phosphate. Right? We've activated it to be sort of an electrophile. All right, and so in fact, the next steps of the reaction involve the phosphate actually acting as an electrophile. Now you might think that the nucleophile would be GDP, but it's not. The nucleophile is actually, the next reaction involves a histidine residue in the active site of the enzyme. And so the histidine is actually going to react with this phosphate. And the phosphate is going to be transferred to histidine. So the reaction is nucleophilic attack by the histidine and displacement of succinate. So succinate the product, and now the phosphate is attached to the histidine. Which is attached to the enzyme. And so this is another kind of high energy compound that this is the only example we'll ever see. But you have a direct bond between the phosphorus and the nitrogen. It's a little bit unusual. So this sort of again preserves the energy of the anhydride, and the phosphate is still in sort of reactive form. And now this can react with the GTP or the GDP. And so the very last step would be nucleophilic attack by the GDP on the phosphorus, displace the histidine residue, and that'll finish the reaction. Finish it here. That'll produce a GTP. So that's the mechanism. It's a stepwise reaction. There's no hydrolysis. Again, it's a stepwise, always preserving the high energy thioester until finally the GTP is made, which still has that. So what was the overall reaction? So the overall net reaction is succinyl-CoA plus phosphate gives succinate, or phosphate plus GDP to give succinate plus GTP, and plus CoA. Yeah, so the substrate of the reaction is succinyl-CoA. Succinyl-phosphate is an intermediate. It's formed in the active site of the enzyme, but it's then used in the very next step. So what I just wrote here on the board is succinyl-CoA plus GDP plus phosphate, makes succinate plus CoA plus GDP. That's what we had. So I want to describe one kind of experiment that was done that was consistent with this mechanism, and I suppose provided some of the evidence for this mechanism. The kind of experiment is referred to as an isotope exchange experiment. I think this was done in several different forms, this enzyme, but I want to describe one set of experiments. So the experiment was to take the enzyme, succinyl-CoA synthetase enzyme, and so if you mix it with succinyl-CoA phosphate GDP, the whole reaction happens. But you don't have to put in all the substrates to get sort of a partial reaction. And so in fact, if you mix the enzyme only with GTP and nothing else, it can't catalyze a complete reaction. But if you look at the mechanism up above there, it can sort of get started. Now, GTP is a product, so when I say the reaction can start, what I mean is the reverse reaction can start. Right? Remember, enzymes always catalyze reaction in both directions. So if you just mix the enzyme with GTP, It'll bind the GTP, and if it can do anything, it'll do it. Right? All right, so the actual experiment was to mix the enzyme with GTP, and include some GDP, and this is GDP star, which means that it contains radioactive phosphorus. The radioactive isotope of phosphorus is P32. So you can buy GDP where one or the other of the phosphorus atoms is actually radioactive phosphorus. And the reason you do that is it's very easy to detect radioactive molecules. So you mix the enzyme with your GTP and GDP, and you let it sit for a while, and then you see what's in there. There's no CoA, there's no succinyl-CoA, so it can't do the whole reaction, but what can it do? You let it sit for a while, you incubate for a while, and then you analyze the mixture. And what you find is some GTP, which is now radioactively labeled. Okay, so somehow you started, all the radioactive label was in the GDP originally, but now you have radioactive labeled GTP. So let's say that was experiment number one. If you do the following two things, you could also take the enzyme plus this phosphorus, non-radioactive phosphorus, and include some radioactive GDP in that. Mix them together. Don't add anything else. Incubate for a while. And what you find is that nothing happens. There's no change. You analyze the mixture at the end, and all you've got is radioactive GDP and phosphorus. There's nothing else. Nothing happened. There's nothing. Right? So, and then another one you could do is this one. So again, you mix the enzyme with GTP like you did before, and now you add inorganic phosphorus where this now is radioactive. You incubate, and again, I say there's no change. You analyze where is the radioactivity in the mixture, and at the end, all you've got is radioactive phosphate. Right? There's no radioactive GTP. Right? So it's only in this mixture number one where something happened that you could detect. Right? And the something that happened is that you ended up with radioactive labeled GTP. Right? So the question is, and I'm not going to go through this, but if you follow the reaction, so this was done at some point, and it's not like this is the only experiment that's ever done. Let's assume this is the mechanism. What you should do is think about what would happen in each of these mixtures to explain why in mixture number one you get radioactive GTP, whereas in these other two mixtures nothing happens. Right? And the answer is, again, you have to think about the reverse reaction. The reverse reaction is exactly the same steps as the forward reaction, just happening in the reverse order. And so if you follow these steps starting here and going backwards, you should be able to explain why we get this result. And I should say that this kind of experiment is often done, and this kind of experiment is often used to provide evidence for an intermediate in which part of a reactant is covalently bonded to the enzyme. Right? You could imagine other ways to explain this, but the simplest explanation is usually that you get a covalent intermediate of something stuck to the enzyme. So you have to think about things bind, reaction occurs, things come off the enzyme, right? They leave the active site, things come back in the active site, reactions occur, et cetera, et cetera. So I don't have time to explain this. So the question is, so this is, so mix the enzyme with these two things. They didn't put in anything else. Right? So there's no, for example, there's no coenzyme A. I guess that's the main thing. There's no succinyl-CoA, there's no coenzyme A. If you leave those things out, then the reaction can only proceed part way. And that's really the key, is that it'll start, if it can, it'll start. But it'll stop when it meets the next thing that's left out. Right? But remember, these reactions can go in both directions. All the steps are reversible. It's not like it just stops and it just sits there doing nothing. So think of all these steps up here. I showed the arrows in one direction, but they're all reversible. Right, so that's an at-home quick question. Yes.
If you did a fourth experiment that was the enzyme with GTP star and GDP, would you also expect to find
GDP star. So you let's add this as a question you can think about at home. What if you did this? You analyze the mixture, and again, the analysis is you figure out what's in there and is it radioactive or not. So the question is, would anything happen in this mixture? So again, if you follow the steps. Now, one thing about this is it sort of depends on where the phosphate is. So GTP, let's assume it's there. Now, if it's not there, then maybe the answer would be I don't think, for this experiment, I don't think it matters where the phosphate was. But I think for this experiment, it depends. If the radioactivity were here or here, you might get a different answer. You think about that. Any other questions? It has to do with, if you just follow the steps of this reaction, that's really what it is. Let's assume this is a mechanism, and then think about what's happening at each step. So anything that happened in this reaction can happen.
Oh.
GDP that has radioactivity. So that is not it.
That's another question.
What?
Number.
For sure.
All right, so the rest of the pathway, fortunately, is much simpler. In a way, simpler.
Yeah. Thank you, Charlie.
I think what is step 5? Succinate. That is step 5.
So let me point out that in this, what I call phase 2, we've made the 2 CO2s, we've made 2 NADHs, so these 2 arrows represent the 2 NADHs from these 2 enzymes. We made this GDP, and let's say succinate is really part of this phase, let's say. And so the last part of the phase is just to regenerate the oxaloacetate. So we started with an oxaloacetate, which citrate synthase used it, and so that this can be a cycle, we have to regenerate it. So let me sketch out this sequence of reactions. Now let's start with succinate. So that's succinate, 4-carbon dicarboxylic acid. And the goal is to convert succinate to oxaloacetate. And so that, to remind us, is oxaloacetate. So this is an oxidation process. As I've drawn it, this carbon has to be oxidized to the carbon. So turns out we have to take 4 electrons out, so there are 2 oxidation steps. So the first oxidation step is catalyzed by the next enzyme in the pathway called succinate dehydrogenase. And so succinate dehydrogenase is going to oxidize these two carbons and will make this as a product. This is called fumarate. And these oxidizing agents, so this is an overall oxidation reaction. These two carbons have been oxidized. So the oxidizing agent that's shown on the slide is, they don't show FAD, but they show the oxidized product. So FAD is the oxidizing agent, and FADH2 is the product. So FADH2, remember, has 2 electrons, and it also has 2 protons, right? So the 2 protons that were removed from here are contained in the FADH2. Okay, so that's the first oxidation step. That makes the FADH2, which we think of as a product of this cycle. Now we have fumarate. We need an oxygen at carbon number 2, and so that oxygen is put in by an enzyme called fumarase. So fumarase uses fumarate as a substrate. The reaction involves nucleophilic attack by water on that carbon and protonation. So this reaction is reversible. This one. The reverse reaction would be an elimination reaction. So this is a hydration reaction. And this makes this intermediate which is called malate. And now we're just one step away from oxaloacetate. To get to oxaloacetate, now it's the kind of reaction we've seen many times. All we have to do is oxidize a hydroxyl group to carbonyl. Right? And so that's the last step of the pathway. Also reversible, catalyzed by malate dehydrogenase. And this is where we make the last NADH. So there's the third NADH. So that regenerates oxaloacetate. This oxaloacetate can be used to make another citrate and start the cycle again. I just want to mention 2 things about this sequence of reactions here that took us from succinate to oxaloacetate. If you look at the overall sequence of reactions, you can say that what happened was in succinate we had 2 CH2 groups next to each other, and the overall process was oxidize one of the 2 CH2s to a carbonyl. Took 3 steps. First step was an oxidation using FAD, then a hydration reaction, then an oxidation using NAD, right? I just mentioned this because the sequence of reactions actually occurs several times in metabolism, and we'll see it again. And I think there's more than one pathway. I think there's only one that we'll see. But I want you to remember this because we'll see a sequence of reactions that does exactly the same thing. Maybe next week. So remember this. Yeah. Remember everything. Remember that.
Yeah.
The other thing I want you to remember, we're going to come back to it. So FAD is oxidized, is reduced to FADH2, and they show the FADH2 is sort of a product, and I keep saying it's a product of this pathway, right? But remember that there were 2 other enzymes that we saw that had FAD as a coenzyme. Alpha-ketoglutarate at FAD, and pyruvate dehydrogenase here at FAD as a coenzyme. Remember the FAD in those reaction mechanisms, go back to pyruvate dehydrogenase. The FAD was a coenzyme. It was bound tightly to the enzyme. It got reduced to FADH2, but the electrons in the FADH2 had to be given up to regenerate the active enzyme, right? So for pyruvate dehydrogenase and that dehydrogenase, the electrons go from FADH2 to NAD to make NADH. And the NADH is the actual product, right? So here, NADH is a product. So what about here? So FADH2, in fact, is not a product. This FADH2 is a tightly bound coenzyme. Right, so this reaction catalyzed by this enzyme is not done yet. And it's not finished until chapter 19. Right, so those two electrons have to sit there. Now I think I'm going to do chapter 19 next, so it's moving too long. But let's remember those electrons. Okay? So in fact, it's okay to say that FADH2 is a product of the citric acid cycle, but in a way it's not. So we'll come back to that and I'll point it out when I do. Okay, so that's the citric acid cycle, yes.
Does the citric acid cycle ever take itself as just a NaDH, like the pentose phosphate pathway did? So like,
I would say that you could say that when acetyl-CoA is coming in, the function of the citric acid cycle is not to make CO2, it's to make NADH.
so the cell has to
Yeah.
produce NaDH?
Because remember that NADH that's being made is going to react with going to be reoxidized by oxygen, which is going to provide energy and make a lot of heat. So the NADH and the electrons in FADH2 are what matters. The CO2, it's a waste product. You can get rid of it. Any other questions? All right, I want to introduce a couple of other things about this pathway that are described in chapter 16. So the first is the anaplerotic reactions in the glycosyl cycle. I don't want to go into a lot of detail on these, but I do want to mention a couple things about them. So the anaplerotic reactions. Anaplerotic, I think if you look in the book, it's a Greek word or something means filling up. Right, so an anaplerotic reaction sort of fills up the citric acid cycle. And so here's a complicated figure from flow. Here's the citric acid cycle in the middle of it. And you could say that one of the functions of the citric acid cycle is to oxidize acetyl groups to CO2. It's not shown. And that, I would say when the entire cycle happens, that's the function. And of course, the making energy. Right? But a lot of the intermediates of the citric acid cycle are involved in lots of other metabolic pathways. And so, for example, citrate I've mentioned is used to make fatty acids and also sterols like cholesterol. Alpha-ketoglutarate is used to make glutamate, which is then used to make other amino acids and oligopurides. Down here, we won't ever talk about this, but oxaloacetate we saw is used to make glucose. Oxaloacetate can be used to make these amino acids and indirectly these amino acids. Right? So these intermediates, especially oxaloacetate, citrate, alpha-ketoglutarate, are really important as starting points for lots of other metabolites. So the idea of these anaplerotic reactions is let's consider the following situation. Consider a cell, and it's using oxaloacetate to make aspartate. Or maybe it's a liver cell, it's using oxaloacetate to make glucose. Or it's using alpha-ketoglutarate to make glutamate and other amino acids. So let's say it's doing some of these pathways that take citric acid cycle intermediates and use them in other ways. Right? And then let's suppose that the cell gets a lot of glucose, and it does glucose to pyruvate glycolysis, and then it makes the pyruvate into acetyl-CoA. And now it wants to do the citric acid cycle, or at least make citrate. And so the next thing it wants to do is it wants to take the acetyl-CoA and combine it with oxaloacetate to make citrate. idea is that if the cell has been doing this kind of metabolism, right, it's used all its OA to make glucose and make aspartate. So there can be situations where the oxaloacetate concentration is quite low in the cell. So let's assume that that's the situation. The cell has used up all its oxaloacetate for other things. Now it wants to do the citric acid cycle. So the thing about the citric acid cycle is that you can think of well, here's the thing. You start with oxaloacetate, and it ends. You get that oxaloacetate back. So you don't use up the oxaloacetate for the citric acid cycle. On the other hand, the more oxaloacetate you have, the faster the cycle can work, right? Because if this concentration is very low, then the citrate synthase reaction will be slow, right? So there might be situations where the cell wants to boost its supply of oxaloacetate, let's say. So it needs ways to do that, and the citric acid cycle doesn't do it, right? Because you don't make any oxaloacetate by the citric acid cycle. So you need ways to make oxaloacetate. And so there are three important ways to make oxaloacetate independently of the sequence of reactions. And one of them is a reaction we saw a while ago. Right? So one of them is this reaction. Pyruvate plus bicarbonate to make oxaloacetate. And so we saw this reaction a long time ago. We saw it, and we said the reason to do this reaction is for gluconeogenesis, right? But as far as the cell is concerned, it can do this for whatever reason it wants to. And one reason might be to make the oxaloacetate as a way to allow the citric acid cycle to be fast. Right, so this is an anaphylaxis reaction. It fills up a citric acid cycle intermediate. Right? So what enzyme was this? This was pyruvate carboxylase. Remember, it used biotin as a coenzyme, and it used ATP that made ADP phosphate. Right? So this pyruvate carboxylase, you could say, has two metabolic functions, at least two. One is, well, it's to make oxaloacetate that could be used for gluconeogenesis, but it's also to make oxaloacetate so the citric acid cycle can get going. Again, that's the idea of an anaphylaxis. Right, so in the book they show 4 such reactions. I think here's the 4 of them. So here's pyruvate carboxylase, taking some pyruvate and diverting it to AA. Another one is PEP carboxykinase, which again is from gluconeogenesis. And in gluconeogenesis, that reaction goes from oxaloacetate to PEP. But it can also go back in the cell, depending on the concentrations in the cell. And so that might be another way to regenerate, to make more oxaloacetate. This enzyme is an unusual one. PEP carboxylase is found only, I think, in some plants. So I don't think it's found in humans. So it's but this last enzyme down here, the so-called malic enzyme, is another one that I just want to mention. And malic enzyme, as shown in this slide, is a way to make malic and to make it from pyruvate. The reaction in the direction indicated on the slide is to take pyruvate and bicarbonate, use that to make malate. So it's a carboxylation reaction. This one does not involve biotin, it turns out. But also there's an overall reduction reaction. The carbonyl is reduced to hydroxyl. The reducing agent is either NADH or NADPH. And I believe that an individual enzyme will use one or the other. I because some enzymes use one and some use the other. But this is how this reaction would occur. And let's see, the other product would be NAD plus, or NADP plus. Right, so this reaction apparently can go in this direction, pyruvate to malate. There's no ATP involved, there's no biotin, as I said. And so that's probably important. It's another way to make a citric acid cycle intermediate. Right? This reaction is also important in the reverse direction. Let me just comment on the reverse reaction, because the reverse reaction is, again, something that we've seen. The reverse reaction takes malate and decarboxylates. Right, so malate is a beta hydroxy acid, and so you make this an intermediate oxaloacetate bound in the active site of the enzyme. So this is where the NAD or NADP would be used. Right, so you oxidize the carbon to a carbonyl. This is an intermediate of the reaction, but now this can decarboxylate. That makes pyruvate, and you get CO2, but in water, CO2 becomes bicarbonate. Right? This is an important reaction in this direction. Right? So this is the same malic enzyme. This is going to be important in the clicker questions coming up. I think this is a really important enzyme. The reason is that now this reaction is going in the reverse direction. What you're doing is you're taking a citric acid cycle intermediate and you're taking it out of the citric acid cycle in the form of pyruvate. Pyruvate can be made into acetyl-CoA, and then that can be put back into. So what it allows you, gives you a mechanism to do is to take the carbon atoms of these intermediates and make them into CO2. And so that's important in some aspects of metabolism. Illustrate